Bohr's theory of the hydrogen atom. So we have emission spectra, which can be either continuous or a line spectra of radiation emitted by a substance. So a line spectra is the light emissions only at specific wavelengths. Every element has a unique emission spectrum. So in the picture we have a gas that has high voltage going through it, or energy. So we're exciting the atoms. As they become excited, they fall to their ground state and they start to emit photons. And if we send those photons, or light, through a prism, we can separate them into the different colors based on their wavelength. Well, every element, every compound has its own unique emission spectrum. So it's one way that we can determine what element or compounds a substance is made out of. So we can apply this especially in atmospheric sciences or astronomy. When we look at the sun, when we look at different planets or faraway stars, we can use the spectrums that are given off by those types of light to determine what the sun is actually made out of. So we have a Danish physicist, Neils Bohr, who presented a theoretical explanation of the emission spectrum of the hydrogen atom. It was believed that the electrostatic attraction between the proton, the positive proton, and the negative electron would pull the electron inwards, and so what is holding the electron out? Well, it would be the force of the outward acceleration due to a circular motion. In other words, they believe that the electrons circled the nucleus in rings, kind of like our planet circles the sun in the solar system. Well, Bohr stated that the electron is allowed only in certain orbits, so there's actually specific mathematical places where the electron can be found. And because those places have specific energies, it's said that the electron is quantized. It has a specific amount of energy. Now, if you change what energy level it's on, you would then change the electron's energy. So Bohr attributed the emission of radiation by the energized hydrogen atom to the electron dropping from a higher energy orbit to a lower one, emitting a quantum of energy. So he came up with a mathematical equation here. Energy of the orbit, so n is your principal quantum number. It's the energy level you're on. It has values of 1, 2, 3, 4, so on and so forth. Equals negative RH, which is the Rydberg constant, 2.18 times 10 to the negative 18, times 1 over n squared. So again, there's your integer, there's your principal quantum number. So the ground state is the lowest state of the system, and when we say system, we're talking about the atom. The excited state then is higher energy than the ground state. The radius of each orbit in Bohr's model depends on n squared. So as n increases, the orbital radius increases very rapidly. The higher the excited state, the farther the electron is from the nucleus, the less tightly it is held by the nucleus. So it's kind of like if you think about a ball on stairs. In order to make our ball go up the stairs, we have to give it some energy. But when the ball falls or rolls down the steps, it can release a bunch of energy because it won't take energy for it to fall. So radiant energy absorbed by the atom causes the electron to move from a lower energy state to a higher energy state, or from a ground state to an excited state. Radiant energy in the form of a photon is emitted, released, when the electron moves from a higher energy state to a lower energy state. The amount of energy involved, either to gain or to lose, is determined by the distance between the beginning and ending levels. So for the red here, going from this state to this state, we're going to release one amount of energy. When we go from the third to the first, we're going to release a second amount of energy. They're not necessarily equal because we're talking about the distance between the beginning and the end transformations. So mathematically, we can all put this together. So the change in energy from the final to the initial, well, if we determine or we use Bohr's equation, the Rydberg constant times 1 over n squared for the final and the initial, then we can subtract them to get the overall energy change. to simplify this equation, we can take out Rydberg's constant to the outside of the parentheses, which would allow us to drop the negative off of there as well. But we also know that energy is equal to Planck's constant times the frequency. So really, energy equals h nu, and then energy equals the change in our energy levels are really, we're talking about the same thing. So if you look at the hydrogen atom and the emission spectrum that the hydrogen atom gives us, we have different series. So Lehman series, Balmer series, those are named after the scientists. All four of them are named after the scientists that studied that series of lines for hydrogen. The Balmer series is probably the easiest one for us to understand because that's the one that falls in the visible spectrum. So when our electron falls from the third to the second energy level, we're going to see a red colored light. When it goes from the fourth to the second, we're going to see a green colored light, so on and so forth. So that's why that one we usually focus more on than the other three, just because we can see it. So what is the wavelength in nanometers of a photon emitted during the transition from n is equal to 6 to n is equal to 4 state in the hydrogen atom? So if we use the Rydberg constant here, we would have our energy is equal to 2.18 times 10 to the negative 18 joules times 1 over our initial energy state squared minus our final energy state squared. So we have an energy value of negative 7.57 times 10 to the 20th, negative 20, joules. So the only unit we have here is joules, and that's what energy is meant to be in. Notice that it is a negative value. Why is it negative? Well, our electron is dropping in energy level, or falling in energy level. So our energy should be emitted. We should be releasing this amount of energy. Well, now that we know we have this amount of energy, we could then calculate the frequency. We could also calculate the wavelength of that transition, so we would know what kind of energy it's being released or what colored light it might be releasing. So the electron actually has a dual nature. So why is the electron in Bohr's model restricted to orbiting the nucleus in fixed distances? De Broglie reasoned that if light waves can behave like a stream of particles, or photons, then electrons should be able to possess the wave properties. So the electron is bound to the nucleus. It acts like a standing wave. So if you look at the first picture, it's like here's our electron, here is our nucleus, so we have our wave going in between. The nodes, the electron and the nucleus, and the amplitude is the amplitude of the wave at those points. At those points is 0. That should say points, not pints. So the amplitude here is 0. The amplitude there is 0. The greater the frequency of vibration, the shorter the wavelength of the standing wave and the greater the number of nodes. So if we go back, you can see how changing the wavelength, here it's the longest, then it gets shorter and shorter. We're adding a node, we added 2 nodes, and the frequency increases. The length of the wave must fit the circumference of the orbit exactly, or it would partially cancel itself on each successive orbit. So the relation between the circumference of the allowed orbit and the wavelength of the electron is given by the equation 2 pi r, where r is your radius, equals n times the wavelength. Remember, n is your energy level. It's the integer 1, 2, 3, 4, all the way up. So the energy of the electron then depends on the size of the orbit, and so the value must be quantized. So the farther away from the nucleus you get, the larger the radius, the more energy our electron is going to have. De Broglie's reasoning led to the conclusion that waves can behave like particles, and particles can exhibit wave-like properties. So our equation then is lambda equals h over mass times velocity. So there's that funny looking U again. This implies a particle in motion can be treated as a wave, and a wave exhibits properties of a particle. So you have a duality there. Duality acts like two things.
Ashley King, please report to the main office. Ashley King, please report to the main office.
So calculate the wavelength in nanometers of a hydrogen atom, which gives us a mass, moving at, and it gives us the velocity. Well, here's one problem. The velocity is in centimeters, and we need it to be in meters. So I know there's 100 centimeters for every meter. So that would give me 7 meters per second. So I want to calculate the wavelength. So the wavelength equals Planck's constant divided by my mass. And we do want the mass in kilograms because a joule is kilogram per meter squared, meter over second squared, times our speed in meters per second. Alright, so our seconds would cancel, our kilograms would cancel, remember joules is really kilograms meters over seconds, so that cancels. Our seconds we already said cancels, this is squared. So we're left with just 1 meter. So our answer would be 5.65 times 10 to the negative 8th meters.